Welcome back, ladies and gentlemen. We're going to be talking about exponential and log equations now from section 3.4. What we're going to work on is solving equations involving exponents and or logs. And just one little note there about our book. We're going to round to 3 decimal places anytime our answer is a little bit messy. Alright, but basically the equations break, at least in my opinion, into 4 categories. We've got exponentials where a common base is possible. And sorry, I got an extra parenthesis in there. Please ignore that. Alright, anyway, so for example here, and this one's a little bit on the easy side, and this will be the last easy one of this video, but we've got e to the 2x equals e to the x minus 7, so this is the classic duh scenario. Okay, well of course that means that 2x has got to equal x minus 7, and pretty simply that gives me x equals negative 7. Alright, so yay, yippee, yahoo! Alright, so again that's the duh scenario, and that's the last easy one you're going to see for a while. Okay, now it's possible that the common base is possible, it may just not be very obvious from the beginning. So looking at this, I've got this very messy looking thing, and please fight the temptation to multiply the 5 and 3 and get a 15. Of course, if you do that, Aunt Sally will be oh so upset with you because you took care of a multiplication before the exponent. But anyway, so first thing first, you divide off that 5 to avoid any relative upsetting. Then we've got 3 to the x, parentheses optional at this point, equals, let's see, 40 divided by 5 is an 8, 5 divided by 5 is a 1, so whoo, that looks fun. And hopefully without too much effort from that point, now you notice the common base and you can get to x equals 4 without too much yelling and screaming. Okay, our second category of equations is exponentials where the common base is not possible. Okay, again, you might start with a semi-messy looking setup, and, you know, hey, such is life. Again, can't multiply the 12 and the 5, so we'll divide the 12 off. And now we'll be looking at 5 to the x plus 3 equals, well, 9 over 12, you can reduce that to 3/4, or if you're decimal inclined, we can go with 0.75, so basically whichever of those two you prefer. I'll go with 0.75 just for the sake of argument, but there you go. Okay, now at this point, I can't turn 0.75 into 5 to some power, at least not a very nice one. So I've got something else that I've got to figure out to do. Okay, and that thing, I actually disagree with the book a little bit, although the net result is the same, so you can kind of pick your own choice here. But what I like to do, well, let's do this. The book likes to take the natural log of both sides every time, no matter what the bases are. And that works just fine. What I like to do is I take the log of whatever base this number is here, so in this case 5 of both sides. So log base 5 both sides. Okay, now the book uses natural log, and you end up with natural log 5 to the x plus 3, and to me it's just kind of messy. What I like doing here is, because of our inverse property with logs, since these two numbers match here, the 5 and the other 5, they cancel out completely and leave us just simply with the x plus 3. So basically it clears up the whole side very quickly that way, which is why I like it. But anyway, we got log base 5 of 0.75. Okay, what the book likes doing with natural logs is, because now on the other side they have natural log of this, and all they have to do is punch a button in the calculator. The good news is, for folks with the Inspire, you can type that in the calculator just fine. Folks without the Inspire, you actually have to use that change of base formula now, which is, I think, why the book likes doing what it does, as opposed to the way I like to do it. But choose your own method. But at this point I've got x plus 3, and then again I can use my change of base formula or whatever, and this works out to be negative 0.1787 and a whole bunch of key decimals. Alright, so at this point of course I just have to subtract 3 from both sides, so I get x equals negative 3 point icky decimal. Okay, and again, if you remember from earlier, the book is going to round to the 3 decimal places here, so I've got negative 3.17, and then the 8 rounds up to a 9. So this is the final answer that you would see in the book for this problem. Alright, the book is going to throw you a few different curveballs as far as the ones that don't have matching bases, but I'm just going to kind of pick one and run with it, and if you have questions on some of the others that trip you up, please ask and I'll be happy to help. Alright, but anyway, looking at this one, this guy looks, well, maybe that's something that could be factorable. And if you like that u substitution trick, of course you go with u equals e to the x, and then from there basically what you're looking at is u squared minus 6u plus 8 equals 0, and hopefully that's easily factorable. Basically I skip the substitution and go straight to the e to the x as the front half of both parentheses. and then I break up an 8 to make a 6, and of course that's going to be a -2 and a -4. Okay, from there, of course, since I've got something factored now and equal to 0, I can break that up into two little equations. So e to the x minus 2 equals 0, and e to the x minus 4 equals 0. Okay, and now I'm going to add the various numbers of both sides, get e to the x equals, and I'm purposely going to leave a little space there, and get 2, and e to the x equals same thing, leaving a little bit of gap, you get a 4. Okay, so from there, okay, the book's method, my method will be identical here, because the book always uses natural log, and I use natural log when I see a base of e. So, kind of by coincidence this time, we're both going to do the same thing. So, there we go. So in both cases, I would take natural logs on both sides. And then again, the whole point of that is the natural log, because that's base e, cancels out this e and then the log itself, and basically leaves you with the x. Okay, and then basically just type in natural log of 2 in your calculator, and it works out to be 0.6931 and a bunch of other decimals. Same thing over here. I get an x on the left, and the natural log of 4, type in that in my calculator, gets me a 1.3862 and a bunch of other decimals. But again, our book's directions are going to be round to the 3 decimal places. And so I get x equals 0.693 and then 1.386 as my two very, very messy but very correct final answers. Alright, our next category is log equations with a mix of logs and regular numbers. So this is the first time basically the word log happens in the original equation, and so we need to work with that. Okay, now first thing first, I want to try to get that log by itself. Okay, and again, please resist the temptation of turning that 8 plus 3 into an 11. That would make me very, very sad. So first of all, we're going to subtract the 8 from both sides, giving us 3 log base 2x equals 5. And then in an unfortunate set of circumstances here, as I divide off the 3, I get log base 2 of x equals an icky fraction-y sort of thingy, so 5/3. Okay, but don't worry, fractions need love too. Okay, now right here you might be thinking, oh my gosh, I'm stuck. But if you remember, we can take equations in logarithmic form and turn them into exponential form. Okay, so basically that's what we're going to do here. So take that subscript 2, take it to the power on the other side, in this case 5/3. And then that equals the thing inside the log, which conveniently in this case is the x. Okay, now normally that might be a good answer on its own, but the book is going to ask us for a decimal here. So basically type 2 to the 5/3 into your calculator, and you should get 3.1748 and a bunch of other decimals. But again, with our rounding to the 3 decimal places kind of rule, we got 175. So there you go. Alright, now what we're looking at here is a little messier situation, and maybe it doesn't look that much messier now, but it's going to get that way, so brace yourself. Alright, now what we have here that's different from the last one is I have the word log twice. So basically what we want to do is use our condensing properties to smash this into a single log, and then once it's down to a single log, we could then do those conversions like we did in the last problem, converting between log and exponential form. Okay, so basically here it goes. So since I have log minus log, well, if I have that, I can condense it by turning it into log of a quotient. So my very first thing here is going to go natural log of x over x minus 6 equals 3. Okay, and now I've got a single log equals a number, so I can convert it. Okay, now remember I've got a little subscript 3 in my log here, so this becomes that subscript to the exponent, which is the number on the other side, equals what we have here. X over x minus 6. Okay, now you might have an impulse right now to go to your calculator and type in e to the 3rd, and you're going to get some crazy decimal, but please don't, because that's going to make it worse. Okay, at this point, I've got my standard, well, to me at least, it looks like a cross multiplication equation. So I can imagine a 1 denominator there and cross multiply. So I'll have e to the 3rd times x minus 6 times e to the 3rd equals, well, 1 times x is x. Okay, now we have kind of a dangerous situation here that I've got x showing up more than once, but through the magic of factoring, we can get it down to 1x, and here's how. Okay, first of all, bring every x term to one side and all the non-x terms to the other. So I'm going to leave my e to the 3rd x here. I'm going to bring this x to the other side as a negative x, and I'm going to take the 6e to the 3rd to the other side. Okay, once it's there, again, like I said, I'm going to factor out the x, and now this leaves me the e to the 3rd minus 1. And that still equals the other side, unchanged. And now I can divide off the e to the 3rd minus 1. So I've got x equals 6e to the 3rd over e to the 3rd minus 1. Okay, and now that the x is by itself, this is the time you reach for the calculator. Okay, everybody pretend that's an E. That is in fact one of the droids you're looking for. Okay, now typing that mess in your calculator is a little bit awkward, so I do encourage you to practice that just to make sure you can get all the right parentheses and everything in the right places. And once we do that, pardon me for running out of space, but you should get something like x equals 6.31437 and a whole bunch of icky decimals, but again with our rounding rule we have an effect here. That'll be 6.314. Alright, and so yeah, a little bit messy, but it does work out just fine if you pay attention to what you're doing. Okay, now my fourth and final category of equations here is our log equations with all logs. Okay, so again, I have three different terms and they're all logs. Of course, if it was just log equals log, it's really easy to just drop them. Okay, please don't simply just drop all three logs at once. Okay, that's not how that works. It's got to be a single log equals a single log. If you need me to explain that to you in class, I'll be happy to do so, but for now, let's just go how you should go. Okay, well, again, log plus log means I can just take the two logs, smash them together into a single one by multiplying the things inside. So that gives me an x squared minus 7x. Okay, and now that equals log base 4 of 30. Okay, well now that I have log equals log, the duh property takes over, logs go away, and you're left with a fairly tame looking quadratic. Alright. Okay, and from here of course, you know, just regular stuff. Get a 0 on one side, and then start factoring. So in this case it'll be x plus 3, x minus 10. Okay, pardon me for going fast, but we get x equals negative 3 and positive 10. Okay, however, remember, logs, you can't take the log of a negative, so I have to check my numbers back into my original equation to make sure I don't end up with a log of a negative. And unfortunately, sure enough, that negative 3 is somebody who doesn't fit the program, so we got to get rid of him. Although the 10, plugging the 10 back into both of these guys works just fine, so basically we get to keep him. So final answer is only x equals 10 and not the negative 3. Alright, now we have a problem that looks very similar here to the last one we just did, and I'm actually not going to finish this one, but I just want to kind of give you a couple different options for doing it. Okay, the only real difference between this one and the last one is the two logs on the same side of the equal sign have a minus sign in between them instead of a plus. So basically you can handle this in one of two ways. First of all is kind of deal with it in the sides that they're on, and the subtraction turn into a division. So I'll have log base 6 of x equals log base 6. Okay, again, turn that into a division because it's a subtraction of two logs, 14 over x plus 5, and then again, incorporating our duh property, and then kind of using a little bit of foreshadowing. I realize I have a fraction over here, so I write my other guy as a fraction, and give myself a cross multiplication setup. Okay, from there, I trust you to go from there, so I'll just say etc. Alright, so option number 2, I'll do it here on the right, is, well, you know, it's an equation. I'm free to do anything I want to an equation, including add things to both sides. So if I add this log term to both sides, it'll cancel out on the right and show up on the left as a positive version of it. So basically by doing that, I'll get log base 6 of x plus log base 6 of x plus 5, that's 5, equals log base 6 of 14. Okay, and then basically this looks nearly identical to the last one. Slight variance in the numbers, but all you would do from there is smash it together just like the last one. Log base 6 of x squared plus 5x equals log base 6 of 14. And then notice that's exactly what you would get by doing the cross multiplication there anyway. X squared plus 5x and then 14 on the other side. So there you go, etc, etc, etc. Alrighty, now the word problems that I know you're all excited to see, but here we go. I'll just do one and save you the torture, but here we go. Alright, how long would it take an investment at 7.2% interest to double if the interest was compounded monthly? Okay, now initially you might be like, wait, we don't have enough information, but actually you do. Alright, well, again, our general formula for this, which I don't expect you to have memorized necessarily, but quite honestly, after doing it a few times, you probably should. Looks something like that. Okay, again, the n is the how many times per year interest is compounded, t for time, r is rate as a decimal, principal, initial amount, and final amount. Well, here's the nice thing about this. If I wanted to double, well, whatever my principal is, I want that to be twice as much. And the very first step in solving this problem is going to be to divide by whatever the p is. So if this is a 3, and that's a 6 then, because I double it, I would divide and I'd get a 2 over here as a. And, you know, whatever. So basically, what I'm saying is all I need to put over there is a 2, and then I have a 1 for my p-value, which means I don't even need to write it. So I have 1 plus, okay, now my rate, again, make sure you convert that to a decimal, 0.072, and all over monthly, so that's a 12. And then I've got 12, and then again the question is how long, so I'm not going to know what my time is yet, so there's my t. Okay, now before logs, this is a very, very difficult problem to solve because I've got this variable up as an exponent, so really the only thing I can do is like guess and check. But now with the magic of logs, we can solve a problem like this. Alright, so first thing first, I've got this very, very messy decimal right here, or actually big collection of yuck, so I'm going to clean that up. Okay, I honestly conveniently picked a number that's going to divide nicely here. Depending on the numbers, you might get a very, very messier decimal than what I'm about to, but 1.006 is what happens when we work that out. And then you get your 12t. Okay, now at this point, my rule about using log base whatever my base is a little bit nasty, because then I'd have log base 1.006. And if you want to use that, that's great, but honestly in this case I think I'm going to bend and go with the book's idea of just using natural logs, just because it's a little less awkward to write. So I'm going to take the natural log of both sides here. Alright, now again, the reason for doing that is natural log of 2 works out to be whatever decimal it works out to be, and natural log of this messy thing works out to be something as well. But basically, moral of the story is, I can bring the 12t down out in front, and then I can divide off whatever natural log of that icky thing is, off of the same side as the natural log of 2, that icky decimal, giving me one complete icky decimal of 115.8707 ... forever. Okay, now at this point all I have to do is divide off the 12, and now I have that my final amount of time is going to be approximately 9.6558. Realistically though, I don't think you've ever talked to somebody about 9.656 years of time, so I think rounding to the nearest tenth here is a little more appropriate, so we're going to just go with 9.7 years. Alright, so basically, if you can find yourself 7.2% compounded monthly, that means if you throw $100 in the bank and you walk away from it and come back in a little less than 10 years, you should have $200. Alrighty, well here's the assignment. Okay, I'm sure you probably spotted the word optional there very, very quickly. Basically the 9 through 23 section is some fairly simple equations, although if you're having a little bit of trouble with these things, maybe it's a good place to start to get your confidence up a little bit. The other ones are a little bit trickier for sure. Also in the 9 to 23, the last couple in that chunk are a couple of graphical approach sort of ones, so you can kind of maybe visualize what's going on a little bit if that helps you and you're a visual person. But otherwise, there it is, and I'll see you in class.